Everyone, so we're the SmartFin project. And to give a little bit more of a background, we're from the Engineers for Exploration research group, and this research group primarily focus on environmental and sustainability related engineering projects. So as part of this larger group, SmartFin embodies that, and I hope to give a bit more of a motivation on what the project is exactly and how it came about. So if you go out to Scripps, La Jolla Shores, you see the surf zone, which is the area of the ocean that's closest to the shore. It's a very energetic zone. There's lots of waves. There's lots of servers. There's lots of people. Lots of components involved. So it becomes really hard to sort of monitor this zone. It becomes really hard to put a really big buoy in there to sort of, which is the primary way oceanographers collect scientific data. But what we can do is, so we see all these surfers out there that for most of their time, they're sitting idly waiting to catch the next big wave. And they're sitting idly on a big platform that we can leverage and sort of use as our sensor monitoring and collection platform. So if you take any surfboard and replace the fin that's underneath it with what we call a smart fin, we would be able to leverage that fin and using our sensors aboard that fin to accomplish our goals better.
Uh, so talking more about the sensors that the smartphone is equipped with. So it does this job by having sensors such as the IMU, which is the inertial measurement unit, and that collects the accelerometer, gyroscope, and magnetometer data, the temperature sensor, which gets the temperature, and a GPS, which tracks the position. All this data is then collected by the fin, and it uploads it onto a common cloud through the cellular reception on the fin. And that data is then ready for researchers to use for like any further research. So she's going to talk more about the applications of the smartphone.
Yeah, so we talked a lot about the range of data that our smartphone can collect. So if we here I'm going to talk a little bit more about the potential applications of our smartphone. So we've already talked about how our smartphone can essentially be attached to longboards to collect data, and we hope to leverage this and get passively collect data from our citizens. So our citizen science platform essentially will allow us to give our fins, give citizens access to our fins so that we can passively collect data about these nearshore areas, which scientists and researchers can then use for their research. Moreover, our SmartFin sensors can also very accurately predict sea surface temperatures, especially when it comes to nearshore areas where there are very small changes in temperatures. And we hope that we can use our SmartFin to learn a little bit more about sea surface temperatures in like beach and coastal areas, which a lot of buoys can't do in such crowded areas. And another application is that we hope to use the large surfing community here in La Jolla and also other like coastal areas and learn a little bit more about these surf zone areas and also learn about like the surf session dynamics. And Alex will talk a little bit more about how we can use that.
Yeah, so in our efforts to monitor the surf zone area, while our surfers are waiting for their next wave, we can use the data that they collect to analyze the wave height. And just we do this passively while they're waiting for their next wave. So it's really convenient. And we'll go more into in depth about this in future slides.
So just for record, our work is inspired by this open source work called Open Map Buoy. So it basically places a buoy in the water and there is a IMU integrated on it. So it processed IMU data on board with Kalman filter and 3 sigma filter.
So when we're fairly interested in this, we're not using their algorithm specifically, or at least not in the exact. We're going to use a slight variation, and this is an overall view of how we're going to do this. So the way we're looking at this, right, we have our IMU that provides all of our acceleration, angular momentum, angular velocity, and magnetometer and magnetic field strength readings. These are all taken into a Kalman filter that provides our attitude estimation. We can then use that attitude estimation to reproject accelerations into our global world space, and that will provide us information about the accelerations in our vertical orientation because our fin and our sensors are moving around, so our up axis is not always pointed up. Once we do that, then we can take that acceleration data, that vertical acceleration data, and convert it into our vertical displacement, at which point we can do all of our wave dynamic studies on that vertical displacement information. One of the key things that we need to do in order to use any IMUs or any inertial or any sensors whatsoever is make sure that our axis conventions are reasonable. So one of the things that we've been working on is looking at making sure that the IMUs that we're using for this test are outputting in a reasonable state. And so you can see here we're looking at a 45-degree pitch motion, and those are very readily visible in the accelerometer data. Likewise, that same data shown through the angular velocity information is also clearly visible in our y-axis, and so you can see that significant rotation in our y-axis, rotation back down in our and rotation back down. We see a little bit of rotation occurring in our x and z axis, mostly because we can't control those axes as perfectly, so we can't produce a purely pitch motion in our sensor. And again, if we double check our magnetometer outputs, we see again information corresponding to that rotation around our y-axis. So I'll go ahead and let someone else talk about this.
So we now have the question of how do we take our three independent sensors and merge them together in a way that makes sense? How do we take this data and how do we estimate our wave height as our ultimate goal? So how do we estimate the vertical position of this? So in order to do that, we're first going to kind of target estimating the orientation of the fin. And in order to do that, we're going to use a Kalman filter. So with the Kalman filter, we make some initial estimate of our state, which we're going to say is Gaussian. We often choose Gaussian because it's a good approximation of stuff in nature. And in fact, most of our the readings that you expect to get from most sensors are going to be some value with Gaussian noise, or could be approximated as some value with Gaussian noise. So we're going to take some initial state. With this initial state, we're then going to take some observation, and potentially this observation may be noisy, may not be trustworthy, and we're going to use that observation to predict how our state, in this case, our orientation has changed. We're then going to use some observation, which maybe we trust more, and we're going to use that to kind of correct that. So as we see, by doing this kind of noisy estimation and correction, we can get an estimation that's close to our optimal states. And this becomes ideal because as I'm going to talk about a little bit later, that when you're observing things like acceleration or angular velocity, these tend to have biases and errors, and those errors, especially when you assume that things are deterministic, can become very detrimental. So what does MATLAB provide for doing these things? It provides the two filters that we're going to focus on. The first one's the IMU filter, and this one leverages just accelerometer and gyroscope data. So this is nice because it allows us to get orientation fairly easy, or at least an estimate of orientation fairly easily. But it does have a question: where is north? If I have two boards sitting next to each other, how do I relate their data? So in order to answer that question, we can use an ARS filter, which is, in this case, pulls in magnetometer data as well, which now gives us some estimate of where is north. So through this, we're going to compare kind of the benefits of the IMU. We're going to look at the IMU filter, and we're going to look at the ARS filter, because both do have their benefits. So let's look at the direct filter outputs from MATLAB. We can see the estimated orientation for yaw, pitch, and roll are presented on screen. I'm going to draw our attention to the yaw graph at the top. We can see that our IMU filter, because it has no reference with the magnetometer, is at 0. And that's to be expected here. We now have the Ahars filter at approximately -33 degrees versus the on-chip Kalman filter. So these data are produced. This data is produced from a vector nav, which has an on-chip Kalman filter that also estimates orientation, and we're using that here as our reference. So in this case, our on-chip Kalman filter produces a different result than the Ahars filter. In this case, this is something that is on our future works to kind of investigate and understand why this is. But for the purposes of this conversation, because we're only looking at vertical heave, that is something that we can largely ignore since it does not impact vertical heave. And to kind of give context of this, as compared to the original IMU data, this data is instead, while that data was a 45-degree twist or pitch up, this data is repeated bobs up and down of about 20 centimeters. And we will look at so then we then take this Kalman filter data and we use it to kind of transform the acceleration, our vertical 20-centimeter bobs to world space. Again, because our accelerometer may twist, we want to make sure that we keep this in world space so that we only have to worry about the vertical axes. And in this case, we can see those bobs, particularly in the vertical z-axis of each one of those spikes relating to a bob up and down. So we have this noisy data, and we need to talk about how we move this data from acceleration into first velocity and into position. And the way that we do that is we'll focus just on the c, and we'll integrate it first to velocity and then the position. So kind of going through that, when we get to position, we end up with, unfortunately, this this graph with exponential error. So when our real world was 20-centimeter bobs, we are seeing that our IMU is 90 meters in the air, which obviously is not correct. So this comes back to what I said originally, that the benefit of the filter was that you do not have to assume that things are deterministic. So in this case, when we're doing our integration, our double integration to go from acceleration to velocity and then to position, we are integrating each one of the biases that come from, or each one of the biases and each one of the errors that come from the Gaussian noise. So that first becomes linear in velocity and then becomes exponential in position. So, and I unfortunately don't have a velocity graph here, but in the velocity graph, you can see each one of the spikes of the move up and down. And in fact, here, even though it's not as pronounced, you can see small waves in this that again reflect to those up and down motions. So, question is, where do we go next? We know that this double integration caused bias amplification. We did this as it was closely related, although not exactly the same as what the OpenMet buoy paper that we were originally looking to compare against did, and are now working on moving forward. We need, as OpenMet buoy they had methods of removing some of these errors within the filter. With some of these errors that can be determined. They have methods of getting rid of some of these errors within their accelerometer data, which we have not implemented, and we will do that. We also want to add some additional states into our Kalman filter to be able to, instead of assuming that our acceleration is deterministic, leverage Gaussians to address potential errors in our data. As we stated, as we say with the yaw graph, or with the yaw graph as well, the Kalman filters, the on-device Kalman filter and the Kalman filters for MATLAB are not in agreement, and we are at this point not sure why. Suspect it might be a configuration issue with the vector nav, but we need more time. We need to spend more time to investigate that. As well as So that's for the magnetometer, as well as for the Kalman filter. Again, with our vector nav, we were gain axes in northeast down, and for MATLAB we had to provide it to them in east north up, and we need to again determine what the differences are. Lastly, so the references to the OpenMet GUI. We'd also like to thank MATLAB or MathWorks for their collaboration and assistance on this project.